Comenzamos entonces nuestra primera charla magistral y quisiera invitar al doctor Claudio Meneses, quien va a ser el chair, ya el panelista doctor Chris North. Por favor, doctor Claudio, adelante.
Sí, muchas gracias. Sí, ahora veo conectado a Chris. Ya, ok. Bueno, voy a introducir primero al doctor Chris North, ¿cierto? Lo voy a hacer en español primero y luego lo voy a hacer en inglés para entendimiento del doctor North, ¿cierto? Bueno, para mí es un honor, digamos, introducir al doctor Chris North, quien es un profesor tiempo completo en el Departamento de Ciencia de la Computación en Virginia Tech, ¿cierto?, en Estados Unidos. El doctor North es un profesor, es director asociado del Shanghai Center para inteligencia artificial y analítica de datos, ¿cierto? Doctor North también ha servido como co-chair en varias importantes conferencias internacionales y es editor, digamos, de varios journals de alta calidad, digamos. También es importante destacar, digamos, aparte de su tremendo currículum, ¿cierto? Es destacar el doctor North ha adjudicado sobre más de 15 millones de dólares en grants, ¿cierto? Y también es autor y coautor de más de 125 publicaciones, digamos, todas, digamos, con revisión de pares, ¿cierto? Su investigación tiene que ver con la interacción entre el humano y la inteligencia artificial para el análisis de grandes volúmenes de datos, ¿no? Y bueno, esperamos que cada uno de los asistentes pueda disfrutar de esta muy interesante charla de apertura de la conferencia. Y la organización, ¿cierto?, desea agradecer, digamos, por adelantado la gran disposición del doctor North, ¿cierto?, para aceptar ser parte de esta conferencia. I see Dr. North, he's connected. He's already connected, so it's for me an honor to introduce to Dr. North. Dr. North is a full-time professor in the computer science department at Virginia Tech in United States of America. Dr. North is associate director of the Shanghai Center for Artificial Intelligence and Data Analytics. Dr. North has served as a co-chair in several important conferences, and he's an editor of several high-quality journals. His research seeks to enable human artificial intelligence interaction for big data analysis. Well, we hope everyone can enjoy this very interesting opening keynote talk. And the organization would like to thank in advance to Dr. North for accepting to be part of this conference. So please, Dr. North, you can start your talk whatever you want.
Okay, thank you for that introduction. I'm pleased to join you all today. Buenos días. Just want to make sure that you can hear me and that you can see my screen.
Everything is fine. We are looking at the screen very well. So anytime you have a question or anything, just let us know, and we will maybe translate for you, or anything you need, all right? So just don't hesitate to just tell us.
Okay, yes, thank you. And yeah, thank you for that introduction. And thanks for inviting me to join with you today. Really pleased to be able to talk with you. And actually, on that note, I also just want to give a quick thanks to Brian Keith for helping to make the connection from Virginia Tech back to Chile. Yeah, thank you for loaning him to us as a PhD student. I've enjoyed working with him for the past year or so. And he's working with myself along with Dr. Tanu Mitra at the University of Washington on his PhD, and he'll be back in Chile when he finishes. So thank you for loaning him to us. Really appreciate it. Enjoyed working with him. So thank you. I want to talk with you today about human AI interaction. As you know, AI is becoming more commonplace in many user-facing applications today. I like to make the joke that we probably ought to learn how to interact with AI before it takes over the world, right? But more seriously, it is very much becoming more common for end users to interact with artificial intelligence through various applications like social media, e-commerce, and so on. And it's important that we learn how to design good human AI interactions to support those kinds of applications. Today, in particular, I want to focus on applications associated with data analytics. So how we can use humans and AI together to analyze data. And that comes up in a lot of applications as well. I mean, if you think about even e-commerce, when you go shopping online, you have to sort through a lot of data about products and product features. You have to read a lot of reviews about different products in order to make a decision about which one to buy, right? So even in a scenario like that, there's data analysis going on under the hood. And so the human and the AI have to work together in order to make those decisions, to sort through that data and make a decision about a purchase. And of course, there's other applications in science and in academia and elsewhere, but I think it's an important application domain for human AI interaction. And so I want to sort of scope our discussion down onto that kind of application. So with that in mind, what I want to talk about is how we design the interactions in those kinds of scenarios. And in particular, I want to talk about how we address this problem that I like to call the two black boxes problem. And I'll talk about that first, of what we mean by that. So you've probably heard of the black box problem. This is the idea that from the view of the human, machine learning algorithms are like black boxes, and they're in the sense that they're hard to understand, and the results that they give are oftentimes unjustified. And so it's hard to understand the rationale for why a result is learned from a machine learning algorithm. And you can't see inside, right? And so that's a well-known problem. And so the explainable AI research agenda seeks to address that issue of how to open the black box and understand why the algorithm is doing what it's doing. But I guess I would like to conjecture that that's only half the problem, that in fact the problem is twice as hard as that, and maybe even more, because I would conjecture that there are two black boxes. In other words, from the respect of the machine learning algorithm, human cognition is also a black box. Well, how does the algorithm know what is the human interested in? What is the human's goals and motivations? So how does it see into human cognition in order to get a view of what the human's interests are? And so I like to call that problem explainable CI, explainable cognitive intelligence. Right? How do we know what's going on in the human mind? And so what we really have in human AI interaction is two black boxes trying to talk to each other, both of which are opaque and can't understand the other, right? And so that's a big design problem. So for people like me who come from a human-computer interaction background, that's a pretty challenging problem to work on, how we design interfaces that support communication between these two black boxes. And so today I just want to spend some time talking through some of the challenges associated with enabling these two black boxes to talk to each other, and how, and some example solutions of how we can do that. So I'm going to talk through kind of 5 key problems with associated with the two black boxes. First of all, kind of the overall problem of how we structure the communication. And then secondly, how do we get the information out of the human mind so that then we can send it over to the machine learning algorithm, and how we feed it into the machine learning so that it can act on it. And then how do we get the information out of the machine learning and feed that into the human mind so that the human can act on that. So each of those, there's kind of 5 problems there that we got to work through in the design of this interaction. And I'm going to use what we call semantic interaction as a kind of example of a design approach that we can take in order to solve each of these 5 problems. To do this, I want to focus in on an example. And actually, first, I want to give you a very simple analytics scenario. And I'm going to try to show you a live demonstration here of one of our tools. So this is a system we call Andromeda. It's one of our favorite demos to show human AI interaction in a very simple way. So again, the analysis, the scenario here is data analysis. So we have a multidimensional data set, a spreadsheet of data, and this is just a fun data set that I collected in my class. It's about the students in my class. So you'll see each of these names here is a name of a student in my class. And I took a survey in the class and collected a bunch of data about these students. And the features, the attributes in the data are listed over here. And so for each student, I asked them, how many publications do they have? How many years of job experience do they have? How many places have they lived in their lives? How far they were born from Virginia Tech? All those kinds of numeric quantitative questions, right? And so then we put this into a multidimensional data set as just a kind of a fun data set to play with. And so under the hood here, there's some AI. There's a machine learning algorithm that's doing what we call dimension reduction to help us analyze this data. And so what that means is the high dimensional data is being projected down to 2D so that the human can understand it. And so what we have here is a projection where students that are near each other are more similar in the data. And students that are far away have very different answers in the data, right? So for example, right here, Andrew and Taylor have very similar data values of these values over here. Whereas, for example, Taylor and Chris, that's me, have very different answers. So we're very different in our data, and so they're far away. So this gives you an idea of some of the similarities in the data set very, very quickly, right? So right away, I can see maybe there's a couple of interesting things here. So the AI helps me understand that Chris, myself, is very different from all my students, right? And I can see right away that maybe there's 2 clusters of students here. This cluster looks like, these names look like sort of traditional, English domestic names, right? Whereas this cluster here looks like more like Eastern names, maybe Chinese or Indian names. And so I might posit that maybe these are 2 clusters based on where students are from. Right? And so I start to get an idea of the data set just from the projection. But now I want to be able to interact. I want to be able to pose hypotheses and ask questions to the AI, right? So one thing I might do is try to sort of verify this idea that there's these two clusters based on where people are from. And so I might investigate that by looking at this distance born attribute. So that's the attribute that says how far people were born from Virginia Tech. And so what I could do is just grab that and kind of drag that to the right. And what that means is put more weight on that variable in the distance function that determines the distances in the projection. Okay. So when I drag that to the right, it animates, the machine learning behind the hood is reconstructing the projection so as to put more weight on that attribute than the other attributes. And you can see that, yes, that had the effect of pushing those two clusters apart, right? So now that first cluster is down here and further away from the other cluster, suggesting that, yes, that the fact that these students were born far away is what's pushing them kind of away from these other students that are likely maybe in-state students at Virginia Tech. Right? Now there was a couple of crossovers. If I reanimate that, you'll see that there was a couple of students that kind of moved from the international cluster down to the domestic cluster. Gustavo and Anonymous 3. So not everybody, so that those two clusters wasn't a perfect description, but now I can get an idea that that notion of distance born was an important attribute in this data set and maybe representative of many of the other attributes. Okay, so that's one way I can kind of go in and pose questions and interact with the AI under the hood. But another way, I'll sort of restart from the beginning here and get my original clusters back. Another way is to kind of ask questions that maybe are a little more intuitive for a human, right? So for example, I might say that I might want to know, well, what makes me be like my students, right? Right now, I'm very different from my students, but what would make me be with my students, right? So I can pose that question by just taking my data point and just dragging myself into this cluster and say, what would make me be like those domestic students, right? I can kind of create my own clustering, right? And then I can ask the AI to respond to that and to find a way to support that clustering. So I can click the update button here. And sure enough, it finds a weighting of the attribute space that allows such a clustering to occur, right? And so you can see if I reanimate that here, if I go back to the beginning and you can see how that cluster at the bottom where my name is, it kind of gets even tighter, right? And compresses to a real close cluster. And I can see that what enables that to happen, what enables me to be like those students is distance born and phone minutes. How often do I talk on my phone, right? And I can see that this cluster that I'm in is a cluster of people that are born nearby. So we're from the Virginia Tech area geographically. And we don't talk on the phone very much, right? We don't like to use the phone, probably because we're nearby. So all our friends are nearby. So we don't need to use the phone very much, right? Whereas, a lot of these students up here are from further away. So these are the international students and they talk on the phone more, right? Probably they're calling back home to their folks back in other countries. And then of course, I've also created some other outliers, now new outliers that have replaced me as an outlier, right? In order to make me be like some of those students. So now I can just interact in this kind of thought space, this two-dimensional thought space, and pose queries and hypotheses and get results and learn about the data. And the AI behind the scenes is responding to that by creating new projections that fit my hypotheses. So that's an example of a kind of human AI interaction in the case of analyzing data. And so I just want you to notice how that interaction was very simple and straightforward for me. I didn't have to, I didn't have to know much about the algorithms. I didn't have to type in complex queries, right? I could just interact in this simple thought space and pose questions and get meaningful insights back. So that's a kind of fun, simple example that I like to use just to demonstrate the idea of human AI interaction in data analytics. Today, I want to talk about a little more complex example. And an example we frequently talk about in our lab is one of text analytics. How do we analyze a lot of textual information? And so we do a lot of work with the intelligence community, intelligence analysts, trying to understand a lot of textual information in order to figure out what the bad guys are doing, right? And so we can stop them, right? And so this is a system we call StarSpire, and it enables text analytics, and it has some similar properties to the Andromeda, the tool I just showed you, in the sense that what it does is it takes the textual information and it projects it into a 2D space. So I can begin to see clusters of these different textual documents. I can see which documents are similar to each other, which ones are different based on their contents. And then I can go in as an analyst and start reorganizing that structure, because inevitably the analyst has different, has very more specific interests in the data set and wants to begin structuring that data set according to their interests, right? So an intelligence analyst will start making piles and clusters of documents based on what they think is going on in the data set. Like I might make a pile of documents that are related to maybe one terrorist organization, and maybe another pile of documents related to another terrorist group. And then I might have a document in between that represents maybe some action that occurred between them, right? In order to create a kind of visual space about what I think is going on, right, in the data set. And now under the hood in StarSpire, as the analyst is organizing things, the machine learning is learning about how the analyst is organizing things and helping the analyst do that. So it does two things. So one is, as I organize, it learns my interest and it learns the way I'm organizing, and it uses that to query out additional information that would be relevant to what I'm interested in and put it onto the screen. And secondly, to help me organize that information on the screen. So if I start building a cluster here about one particular terrorist group, it'll go out and find other information about that terrorist group and add it onto the screen and put it in that cluster. So to indicate that maybe that's other information that I should read in order to learn about that terrorist group. So it helps me then form a structure that's meaningful to my analysis. And so that's what StarSpire is all about. And it has this very rich human AI interaction in order to do that kind of analysis. And so that's the sort of running example I want to use as I talk through these 5 different kind of usability problems that I talked about at the beginning. Okay, so with that as a kind of scenario, let's start talking about those 5 problems now and how we could solve them. So the first problem I mentioned in human AI interaction is kind of the overall structure, right? I like to call this question the what is the loop question, right? What is the loop in which these two entities are interacting with each other? What is the structure, the overall structure of that interaction? And what are the roles that the human and the AI take on when they're talking with each other? Right? So we got to sort of first understand this, the overall roles and the structure of the interaction. And in order to do that, what we recommend is taking a human-centered design approach to designing that interaction structure. And so what that means is we first need to go in and really understand what tasks the user is trying to accomplish and what their workflow is, so we can understand how we can fit the AI into that workflow in order to help them, right? And so, so what we did with StarSpire as an example of that is to analyze the workflow of intelligence analysts. And here we had help from Paroli and Card, who had done that previously. And they developed this model of sense making. And so this model is a model of human cognition when people are trying to make sense of a large amount of textual information. And just a quick overview of how it works. This part of the process is what we call the foraging loop, and it's where people are trying to find information relevant to the problem. And then this part of the loop is what we call, what I like to call the synthesis loop, and it's where we start putting pieces of information together in order to create structure about the information. And so this represents the kind of process that humans go through when they're trying to do that kind of text analytics, sense making. And so what we can do is then use this as a guide to figure out, well, how can we fit AI into this process in order to support humans in doing this sense making, right? And so what we did is we took those two major subloops and organized AI algorithms to support those. Namely, we created relevance models to support this foraging problem of finding relevant information to support my analysis. And then we created dimension reduction models that represent this problem of synthesis, of connecting pieces of information, right? Very much like what I showed you with Andromeda, where when I put pieces of information together, I'm expressing something about the fact that those two pieces of information should be considered similar, right? And so I can do some analysis about what would make those similar. And then I can find other information that's similar to those two pieces of information in the same way that they're similar, right? So I'm dynamically modifying the definition of similarity as I'm doing this kind of analysis. And so that what that means is we can computationally model those human thought processes, right, in order to support the human sense-making process. So those are two kinds of models that we built to support this process in StarSpire, and we plug those into the sense-making process in order to help that speed the user along in those processes. Okay, so that gives us then some structure that the human is doing this sense-making process, and we can put the AI in there in various places in order to support that process. And that gives a kind of structure to the human AI interaction. So then we got to get more into the details, right? So that brings up problem number 2 of the explainable CI, the explainable cognitive intelligence, of how do we get the information out of the human's head so that we can feed it into the algorithm and have it respond to the human's needs and motivations and goals and so on, right? And this is a notoriously difficult problem because we know it's very difficult to get people to kind of specify what their interests are to a computer, right? It's hard to get people to externalize their goals, right? People just don't like to take the time to do that. So that creates a kind of usability problem, right? And so one solution here that we applied in StarSpire is the cognitive principle of what we call distributed cognition. And this is a theory from psychology that says that people like to use the environment around them to help them think. Right? So kind of like Andromeda, when I moved those dots around on the screen, that was helping me think about the meaning of those data points, right? And well, it's the same thing here in StarSpire in text analytics. When we observe analysts doing text analysis, what we see them doing is things like making piles, right? Putting things near each other that are similar, connecting things with lines and so on, right? And so what that does is it gives us a kind of view into their cognition. So what I want to do is show you a video of a study we ran where we were observing an analyst doing some text analysis, intelligence analysis problem. We gave them a whole bunch of textual documents and they had to just by hand sort through them and try to understand what was going on in the data set. In this example, they did not have any AI support. It was purely a manual operation. And so I want you to just sort of watch this and watch the user as they work here. I'm playing this back at high speed, right? So this is much faster than the user did it. But what they're doing here is opening documents, reading them, and then organizing them on the screen. And they're doing this all just by themselves without AI support. And you can see how they're beginning to build clusters, how they're beginning to lay out a space to organize the information, how they're connecting things. Maybe you can barely see kind of lines in the background where they're connecting pieces of information. You can see how they're highlighting in yellow some information like down here, and some other information here that they're highlighting. And maybe you'll see some notes. These little yellow boxes here are little computational sticky notes where they're typing in notes about the documents, right? So they're doing all this kind of analysis, just like you or I would do when we're reading papers, in our field, right? And you can see how it's a very dynamic process, right? How their structure changes over time. They move clusters around in order to create structure and in order to define similarity in their own mind, right? And so you can see how they're using this big 2D space in order to help their thought process. So what's cool here is that just by having them do this in a computational setting with a big screen, we actually get a window into their computation, into their cognition. We get an idea of what they're thinking about by watching them act. Okay, and that's the idea of distributed cognition. And so that's going to be very useful for us, right? Because now just by watching them act, we can get an idea of what they're thinking. And therefore we can use that to drive machine learning algorithms to help them. Okay, so this is kind of a neat trick we can use to extract information from their mind without explicitly asking them to tell us what they're doing, because they'll show us. But anyway, just by how they're analyzing the data, right? And so sometimes we like to call this kind of free interaction, because it's things the analyst does anyway to analyze the data, but we get those interactions kind of for free that we can then use to feed into the machine learning algorithm to learn about what the user is doing. So that's one solution to this idea of how do we get the information out of the analyst's head, right? By just watching them organize information in 2D space. Okay, well, let me just say we've explored this idea in a variety of contexts, including big 2D, big screen spaces like this, as well as even in 3D VR spaces. It turns out in VR, people do the exact same thing. They begin organizing into different clusters and things like that. And so regardless of the space that they're in, this idea of distributed cognition is, I think, a really good way to observe human thought in process. So that brings us then to the third problem, which is now that we've got this information, we can see the analyst thinking. How do we feed that into the algorithm so that it can process on it, right? And so the usability problem here is what I like to call sort of a high-level, low-level mismatch in controls, right? So oftentimes in machine learning algorithms, we have parameters that we want the user to be able to control. And we can hook those parameters to knobs, right? And let the user control them. A simple example is, like, if I want to cluster the data, I could use a k-means algorithm. The problem, though, with k-means is that I first have to tell it the value of k before I can run the algorithm, right? It can't run without the value of k, right? And so think about this from a usability perspective. How does the human know what value of k to put? And I think there's sort of two problems. First, if I'm early off in my analysis process, I might not know how many clusters I want, right? So I don't know what value to put for k. And secondly, that's kind of a low-level concept, right? The idea of how many clusters is a very kind of detailed, low-level idea. Humans are typically thinking more high-level, and so forcing them to specify a value of k is sort of forcing them to do something that's lower level than the way they want to think, right? And so it creates a usability mismatch, right? A better example in text analytics is oftentimes we create models that have weights on terms, right? And we create a model that has to do with which terms are more important than others, right? And so what if we then just give a knob for each of those terms to the user? Well, how many terms are there in the English language or the Spanish language? Well, there's thousands, right? We would have to have thousands of knobs, one for each term. But also, users don't want to be thinking about individual words. They want to be thinking about concepts, right? So forcing them to turn knobs on individual terms is too low a level, right? So if we're doing text analytics, the kind of parameters we have in our machine learning models are a mismatch for the way humans think about text analytics. So I like to express that here in kind of an architecture diagram. This is the way StarSpire works, right? We have some textual data. We feed it through various relevance and projection models, in order to create a spatial visualization that then the user looks at. And the question is how do the users manipulate that model? Do we give them a bunch of knobs on these models to turn where they can adjust the weights on each word? That's probably not a good solution, right? So instead, what we do is we create this kind of inverse modeling where the user interacts with the spatialization by moving documents and putting documents near each other and making piles and so on. And we learn from those. So we have to take those kinds of interactions and recast them into underlying parameter model updates, right? So for example, let me give an example here. If the user wants to create a cluster and they put two documents together, they move them together. What can we learn from that from the machine learning point of view? Well, we can analyze those two documents and we can look at, well, what would make those two documents similar? And we can pull out the terms that those documents have in common, maybe co-occurrence, things like that. And we can upweight those terms, right? And so we can figure out what words are important based on how the user is interacting with them, right? And we can do that using heuristics like the one I just described, or we can use some kind of machine learning, right, to extract that information from the documents, right? And so I like to call this, the solution here is this notion of contextualized input. We want to allow the user to interact in the space the way they normally would, but then use the computation to translate that into underlying parameter updates on the underlying models, right? So maybe upweighting and downweighting individual terms based on these high-level interactions, right? So in StarSpire, some of the interactions that we use are the ability to create clusters, the ability to highlight information. When the user highlights something in yellow, we can use that to upweight those terms, right? When the user types in some notes in a sticky note and they take some notes, we can analyze that information and upweight those terms, right? And when the user does searches, if they type in a keyword search, we can use that as a word that we might want to upweight in the underlying models, right? So those are all examples of interactions that the user would normally do and make sense to people. But then we can translate those into parameter updates on the models without the user even having to know that that's what's going on under the hood. So we like to call that contextual input as a potential solution to that usability problem. Okay, so that gets us now, so now we have the information we've extracted from the user's head. We've managed to get that information into the model. The model can now compute on that and update. And now the question is how do we do the explainable AI of getting that information back to the user, right? The new updated information. And so the first problem is problem number 4, which is how do we get that information out of the model and displayed to the user, right? And this is kind of very similar to the previous problem of contextual input. I like to call this contextual output. So the usability problem here is how do we represent the information in a way that is cognitively efficient, right, for the user? How do we open the black box in order to enable them to see the new updates in the model? And so I think the key, at least one key principle here is the idea of contextual output, where we want to display that information in a way that fits into the user's thought space, right? So the user is already working in this 2D, sort of projection space where they're making clusters and organizing information. So let's present the information that comes from the machine learning model in that context so that it's embedded right into the user's thought space, right? And that way it'll make sense to the user. So an example here in the StarSpire, when the user, for example, makes a cluster, like say the user takes this document and drags it over next to this document in order to say, hey, these things are similar, I want to make a cluster here. The system goes out and queries additional information, brings that information onto the screen, and where does it put it? Well, it adds these new documents into this new cluster that the user just created. Right? So the user put these two documents together, And now they see that they have these new documents popping up here that they should also read that would be relevant to those two documents in the cluster that they just made. Right? So by putting that information right there in context, it sort of helps the user know, oh, this is relevant to what I was just doing. I ought to read that next, right? In contrast, when the user put these two documents together, it caused this other document to move a little bit further away, saying, well, this is unlike that cluster you just made, so probably don't read that one next unless you want to do something different, right? So again, it helps to morph the space a little bit and helps the user to find what's the next piece of important information that they should read, right? And it fits it right into their space so that they understand the meaning of these changes based on what changes they're making. So I think that's a very useful principle then to solve this kind of usability problem associated with explainable AI of how do they understand the results? Well, we help them to understand it by putting it in context of their workspace. Right? As opposed to maybe some other examples would be displaying results in some other screen somewhere else, some other window, maybe a list of hits or something, right? You see how that would disconnect it from their thought process. Right? Here's another example. You know, the machine learning algorithms under the hood are learning a weighting on the terms in the vocabulary under the hood. How can we help the user get a feel for what the machine learning believes is important based on the user's interaction? Well, we could give them a big long list of words and maybe a bar graph, right, of the weights for each of the words. But that would be a huge list, right? It would be thousands of words and maybe we could sort them by importance or something like that. But still, these words would be all very disconnected from their analysis process. So again, I think we can apply this idea of contextual output and display that information right in the context of the documents. So what you see here is the documents being automatically highlighted by the model to reveal those important words, right? So the green highlight here is a highlight that the user did. The user said, this is important to me. I think this person's name is very important. Over time, the model has learned some other important words and it has highlighted them in yellow, right? So the yellow is now the system doing the highlighting and telling the user what it thinks is important, right? So it thinks that, for example, this word endangered here, and this organization here called SPOMA is important to the user's analysis, right? It's a little hard to see in the screenshot here, but the yellow has different shades to it. So darker yellow means more important, lighter yellow means less important, right? And words that aren't highlighted at all are not yet considered important. And so this gives the user some additional feedback about what might be important in the documents and directly directs their attention to information that would be valuable to their analysis. So now when the user looks at a document, they can quickly scan to the yellow stuff to find the important information. So you see how that helps them then speed up their analysis. Right? So that's a kind of a neat example of displaying machine learning results in context of the user's task and helping them speed their analysis. Okay. So then the final problem is then so now that the user sees this additional information from the machine learning, how does that information affect the user's thinking? And how do we help the user move their thinking along, right? So how do we integrate that output into their cognitive process, right? And so kind of the problem here is, I like to talk about the usability problem here as a notion of premature formalization. Okay, so that's a fancy word that means if you give the user too much information too quickly, they won't be able to integrate it into their own thought process. And especially if that information is too detailed, too quickly. Right? The way we have observed that human cognition works is in a process that we like to call incremental formalization. people gradually formalize their thinking over time. It's in a sequence of small steps. It's not usually in a big leap of suddenly I understand something. Usually it's in a lot of small steps where I finally come to understand something. And so what we want to do in human AI interaction is mimic that process and help the user make those steps, but help them make those steps faster, right? So they can get to the end result quicker. Here's the key point. If we try to jump them right to the end immediately without making those small steps, they won't be able to do it. They won't recognize that as a solution, right? But if we can help them make those small steps to get to the solution, then they'll understand and they'll see the value in that, right? And so I think a key concept here is that we want to create an association between the human incremental learning and the machine learning model incremental learning. We want those two things to learn together as the sense-making process goes, right? And so we call that incremental formalization. Usually we associate that with cognitive processes. We also want to now associate that with machine learning processes so that the AI and the human can co-learn incrementally together. Okay. And so here's just an example of that we've seen from studies where a user kind of starts with a very rough structure. They gradually begin to formalize things. And finally, by the end, they have a very specific structure with a very specific set of clusters and an arrangement on the screen that helps them then, have a kind of final structure of what they think is going on in this data set. And the AI has kind of helped them along the way to get through these steps very quickly. So that's kind of our last then recommendation on how to structure that kind of interaction in a way that's incremental rather than batch. Right? Okay, so I've got maybe a few minutes left here. So I want to kind of now talk about the outcomes of this. What kind of benefits, when we apply these 5 principles, what kind of benefits do we get? And so I want to talk a little bit about just some of the studies that we've run with human subjects where we've analyzed now people using StarSpire and human AI interaction in order to do text analytics and some of the results that we see. So I just like to highlight kind of 4 key ideas, 4 results. The first one is this idea of trust. And so I think what we've seen here is if we had some sort of magical AI that could just push the answer to the user at the beginning of their process, they wouldn't recognize it as an answer and they wouldn't believe it. And we see this all the time in the intelligence analysis community, that if we just push an answer at them, they tend to be very skeptical, right? But if we have the human and the AI work together in this incremental process, the human is involved in the process, they see the steps, then when they get to the final result, they trust the final result because they were part of it, right? And so I think there's an interesting result here that if we balance the XAI and the XCI, right? If we rely only on explainable AI, probably we won't get very much trust. But if we have explainable cognitive intelligence and explainable AI, if we have a whole loop, then we'll get more trust. So I think the result here is that we want to have a balance, right, of XAI and XCI in this loop in order to enable trust. That's what we're seeing in our studies. The next point is that this idea of high level versus low level. What we've also seen when we talk to the users after they finish their analysis, and we tell them, well, what things do you think were important in the data set? What is your hypothesis? They usually describe it in high level terms, right? Sort of conceptual terms. When we look at the machine learning after the process, of course, we see the weights on terms that it has found, the things that it thinks are important, right? Very low level, right? Individual words, right? But what's interesting is we see a correspondence between the two. And so here's just an example from one of our studies where a user said, well, there's this plot going on in the Caribbean where terrorists are bringing in illegal drugs to the United States through the Bahamas, right? And so the user's thinking in these high-level conceptual terms, where when we look at the model and we look at what terms it's highlighting, well, it's looking at specific locations in the Bahamas, in the Caribbean, right? So like Freeport and Nassau are cities in the Caribbean. And Apple Street is an actual address in Freeport, right? So it's finding very specific details that support the high-level thoughts of the analyst. So we get this kind of high-level, low-level distinction where the analyst is working up here in the high level. The model is helping to fill in the details in the low level in a way that supports the high-level thinking. And I think that's a very useful kind of model to think about how humans and AI can interact, where the humans, it sort of frees up the humans from having to think about all these low-level details, and they can sort of concentrate on these high-level goals and then get help on the details from the AI. An advantage of that, of course, is that it enables efficiency. So what we see is that with these kinds of capabilities, the analyst is speeded along in their process. Just maybe a couple of examples from studies. When we look at the end results of after an analyst has finished their analysis and they sort of talk us through their theory based on the structure they have created in this 2D space, we have found that on average, users put about 32% of those documents in their locations, whereas the AI under the hood did the other kind of 68%, right? So it's about 1/3 human, 2/3 AI in terms of the work they did to create the structure, right? So that's kind of neat that the algorithms saved the user from 2/3 of the work, right? Of just sort of manually organizing things, right? And similarly, in terms of foraging information, of finding relevant information, here it's a little bit the other way around. The user finds about 3/4 of the important information, where the model provides an additional 1/4 of the relevant information, just based on like implicit queries and so on. Kind of another interesting side effect there is that the user tends to find like the core information, like the most important information, whereas the AI tends to find kind of the broader supporting information around their hypothesis. So that's another way that the AI can help, is by broadening the view of the analyst, giving them a little bit bigger perspective. And then I guess the last kind of useful thing we've seen from this is the idea of quantification of bias. That as the analyst works through their process, since the AI is under the hood learning from that process, we can actually look at those models over time and see how the analyst has steered the model, right? And use that as a way to sort of quantify the bias that the analyst has input into the model, right? And, in that sense, I mean bias in both a good and a bad sense. We could use it to say, hey, look how the analyst has got to a good solution, but we can also say, look, they missed these other points in the solution space that maybe we should explore also. Maybe another analyst could go explore those points in the space, or maybe we could direct their attention to some of those points in the space in order to help them make sure they have thoroughly completed their analysis, right? So those are some future work, some interesting new potential features we could add to help analysts do a thorough analysis, not just an efficient analysis. Yeah. Okay, so those are kind of some of the neat results we've seen of enabling this kind of human AI interaction in a very usable way, right? By emphasizing the usability solutions to usability problems. And just a kind of a recap, the key idea is that we want both explainable AI, right, from the AI to the human, but we also want explainable CI, right, from the human to the AI in order to complete the loop, in order to enable those two black boxes to talk to each other. And here's just a recap of those 5 principles that are examples of ways that we can solve some of the usability problems associated with those 2 black boxes. And when we do that, we get some good benefits from doing that. So with that, I will pause and just want to quickly thank all the students, all the graduate students who did the work behind this in order to figure out these cool ideas. So these are just students and alumni from my lab over the past 10 years or so. So with that, I'll open to questions, and I see there are some things in the chat, but if somebody could help with translation, that would be wonderful.
Okay. Well, thanks a lot, Chris. Well, in my case, I can see the question in the chat, but I had several questions. But
Okay, sure.
yeah, well, at least I want to ask you three of them. Yeah, because I found a very interesting topic, a very important topic in the data analytics. One question is about the space to think. So, this is focused in some specific learning tasks, or for example, clustering, or you had support for other learning tasks like classification, like associations. The user can do that kind of tasks in that space to think. Right. That's a fair question.
Okay, so make sure I understand your question. So you're asking, what are the kinds of tasks that people can do in that space to think? Is that the question? Right. Okay.
Right.
Yeah, that's a great question. So typically what we observe just from a cognitive point of view of what people do in these kind of spaces is really what they're working with is the idea of similarity, right? So we observe that people tend to put information close together that is similar, right? And they tend to spread out, put information far away that is dissimilar, right? So they're kind of defining a notion of similarity as they're organizing the information. And that tends to mean, right, that what they're really doing is dimension reduction, right? They're creating a 2D space that represents a high dimensional space in their mind, right? So I think dimension reduction is kind of the primary task, but then there's other sort of tasks that are going on also at the same time, which is they're also creating visual clusters. So sometimes we observe that people like to draw like a circle or a box around a group of things to say, hey, this is a group, right? So that represents a kind of clustering task, right? Sometimes we also see people wanting to draw lines to connect things. And so that represents an association type of task. Sometimes we do observe people labeling groups of information. So they might create clusters and then label them, which you might interpret as a kind of then a labeling for a classification task, right? So yeah, so they are doing a lot of these kind of common, things we think of as sort of machine learning tasks, but they are doing these cognitively in their heads in this 2D space. And I think that was the key insight for us, is when we saw people doing this, we realized that there's this correspondence between what people are doing cognitively and what we frequently do in machine learning. And so we can match those up. And so what we realized is that the 2D space of the screen provided what we call a common ground between the human and the AI, right? Humans actually think in a spatial way, right? They create these spaces to represent their cognition. But also we have algorithms that compute on space, right? We do this all the time. We make two-dimensional projections and so on. And so the 2D space provides a communication means, a medium of communication between the human and the AI. And so that was a really key piece of insight for us when we saw people doing this kind of interaction. But you're absolutely right. I think, future work, a great, research agenda is to explore what other kinds of tasks, what other kinds of common grounds are there, what other kinds of mediums of communication are there. So here we looked at that sort of 2D space, as dimension reduction is kind of the core communication between the human and the AI. But what other kinds of communication might there be? What about tree structures, decision trees and things like that? There's a whole array of other possible ways that people and AI could communicate. And so this is just one of those, the idea of a 2D space as a dimensional reduction space to communicate is I think just one approach, right? And I think there's many more that we could investigate. So yeah, it's a great question.
Dr. Claudio. May I have a question now?
Yep. Yeah.
Okay, thank you. Dr. North, thanks for such a delighted speech based on your research. It's very impressive, for real. And one of the questions of the students that it's like undergrad is asking what is the starting point of learning this field? How they can start learning AI, because machine learning is a huge topic that nowadays is very important because we are using those models to make better decisions, right? And improve businesses. So as an undergrad, how they can start learning machine learning?
Wow, yeah, well, that's a big question.
Yeah, it is.
So first of all, I will slightly modify your question
Please,
because to do human AI interaction, we have to study two fields, right? We have to study machine learning, but we also have to study HCI, human computer interaction, as another field. And we really have to understand both of those fields in order to design good human AI interactions. And that's what makes it hard, right? Because now you have to, right? It's fundamentally interdisciplinary, right? And that's why we have trouble doing it well, right? Because we have to work together in order to do that. Mm-hmm. So I would say both of those fields would be important to learn. How to learn those? Well, sign up for classes, right? Take your machine learning class and take an HCI class and start thinking about how those two ideas would plug together. There's just so many resources out there. So actually, let me bring up a browser here. One resource that I found that's very useful is the various tools on Google. Let me just quickly go to a web browser here. This website called distill.pub has a lot of like really nice examples of kind of explainable AI. And it's a lot of people from the Google AI group published here. And so it makes use of a lot of the Google tools, you know, like PyTorch and all those kind of tools. And so I think maybe just reading through this, it's pretty easy to read. It's designed in a way that's accessible to new students. And so I think this is a good way to sort of get started, but just kind of see what people are doing in machine learning and in explainable AI. And then it has lots of links to other things, you know, so from here you can follow a lot of other links to useful materials. So that's one thing I like to point students to who want to get more into the machine learning and the explainable AI stuff. How to get started in HCI is maybe a harder question. Probably the place I'd start you to look is the textbook by my former advisor, Ben Schneiderman, his textbook called Designing the User Interface. It's kind of the, you know, sort of the core reading, you know, for HCI. So maybe that's a good place to start to just learn about the field of HCI. And then of course that will have one of the nice things about that book is it has lots of pointers, references to other materials out there. So those are two things I would point you as ways to get started. Yeah, it's a big field and there's a lot to learn. Yeah,
and it's very challenging too because it's a field where we always have to keep learning with the new models and technologies and algorithms. So
yeah, it's impossible to keep up, right? So I think you raise a good point. Don't try to learn it all, right? Because you can't, and it's moving so fast. You have to sort of pick a focus and right, you know, like if you want to do image analytics, you know, or text analytics, you know, sort of focus on one topic.
There are a couple of questions that maybe Dr. Claudio would like to maybe just read, and so that Dr. North can respond.
Yes, I think it's a good idea to email to Dr. Norte the question, because we are just in time. Yeah. So I think, Mauricio, we don't have enough time to more questions, right?
Maybe just one of them, and the last one, so that we still like get the flavor of this area that is very like interesting. One last.
Okay. Well,
I think we can take one of the question of the students that are in the question and answers section, maybe.
Yes. The first question that I had: how can we use this technology in a classroom, for example?
Okay. So I think the question is how do we apply some of these tools in the classroom, or how do we teach human AI interaction?
I think it's the first point. How do you apply them?
Okay, great. That's a wonderful question, because that's another sort of favorite topic of mine. So this tool that I showed you, the Andromeda tool, is actually something we use in class all the time to help students learn about dimension reduction. And the way, this sort of interaction can really help students learn it in an intuitive way, right? So they can get kind of the big idea of it before they go down and learn sort of the math, right? So we use this we have used this in everything from young students in grade school all the way up to, graduate students, learning about, dimension reduction, right? And so you might wonder, well, how can I get access to this? Well, it will point you to another website on GitHub. I will see if I can post this into the chat. But that Andromeda tool, we have implemented a version of that in Jupyter. And so you can download it and run it, or you can even use it online here using the binder implementation. So it's a version of that Andromeda software implemented in Jupyter notebooks. And so the nice thing about that is you can see the code and you can see all the math there, but you can also play with the visualizations interactively. So you can see it from an interactive point of view, but then you can also go and learn how it works from a code and math point of view. So I use that in class all the time. I use that every semester in my analytics class to help the students learn about dimension reduction. And so they do a homework using that tool, where first they use it to just analyze some data. And then they have an assignment where they have to modify the tool by changing the code in order to implement a different distance function, right? So they have to change from using, I think the assignment is to change from using an L1 to an L2, distance function, right? And so so that forces them to sort of go in and understand the code and how the math works and figure out which line of code do they change in order to change the distance function and so on. So that's a handy assignment that I use in class a lot of times. And here's something fun. Let me type in one more thing here. Be the data. Find it really quickly here. So I had a student who did this project called Be the Data. And the idea was that we implemented this Andromeda concept using a tracked room. And so the idea is that each student embodied one data point. And then we use the room as the dimension reduction, as the projection, right? And the students would organize themselves in the room in order to create a projection. And then they would get the feedback from the machine learning about, what weights were, what the weights on the dimensions were, right? And so we did this assignment where we had all these young students. These are students that are like sort of 10 to 15 years old, right? So these are young students from the local schools. And they came and they did an exercise where they were analyzing data about animals. And so each student would be an animal. And then we would ask them questions like, well, what makes animals good to eat, right? And so they would organize themselves where, you know, hey, let's put all the good animals over there and all the gross animals over here, right? And then they would get feedback about, you know, domestication or, you know, other features that would make an animal good to eat, right? And then we did a pre and a post survey to measure what they learned about dimension reduction. And it turns out these young students actually learned the idea of like high dimensional data and projection, the idea of that these projections are approximations of the high dimensional space. All these sort of important concepts that we try to teach at the college level, these young students actually learned by using this be the data concept. So yeah, so I would highly encourage using human AI interaction as a way to teach about machine learning.
That is very impressive, if I can mention that. And for sure, I'm gonna download this app and the software and use it, Andromeda. So it looks very...
it's a lot of fun. Yeah.
Promising. So
Yeah. It looks like...
Thank you very much.
Yeah, thanks for having me. I really enjoyed being with you all today.
Claudio?
Yeah, well, yes, I had, as I say before, I had many questions and maybe some kind of research question that I really made to Chris. For me, it's a very exciting topic. So I would like again to send to Dr. Norte for accepting to be part of this conference and to make this wonderful talk and presentation. So, Mauricio, thanks a lot, please.
Muchas gracias, Dr. Claudio. Thank you very much, Dr. Norte, and we will be delighted again to maybe have you in the future in another conference and talk.
Definitely. I have a lot of questions too.
Yeah.
So I would love to visit Chile someday.
Yeah.
Awesome.
Yes. So yeah, I would
All
really
right.
look forward to that.
All right.
Okay. Thanks a lot.
Muchas gracias, Dr. Claudio.